Welcome to Earth Analyst, where the mysteries of space unfold in calm detail. Tonight, we turn our attention to something both rare and extraordinary: 3I Atlas, an interstellar visitor drifting near the orbit of Mars. This isn't just another comet or asteroid. It's a traveler from far beyond our solar system, carrying secrets from ancient regions of the galaxy we may never reach. For billions of years, it journeyed through the silent void, untouched and unseen, until now. As you rest and let your mind drift, we'll gently explore the shocking details scientists have uncovered, the strange possibilities surrounding this object, and why its path near Mars has sparked such curiosity and awe. Settle in, let the universe unfold, and prepare to discover the story of 3I Atlas. The discovery of 3I Atlas came as a surprise to astronomers. At first, it looked like another faint comet, its icy surface reflecting just enough sunlight to be noticed. But as its speed and direction were carefully measured, the truth became undeniable. This object was not bound to our sun. Its path was hyperbolic, a clear sign that it came from beyond the solar system, a rare interstellar visitor drifting silently through the vastness of space. Only to such travelers had ever been seen before, and now humanity was witnessing the third dot as it moved closer to Mars. Scientists realized how extraordinary this moment truly was. Unlike comets that sweep past Earth, this one traced a course near our neighboring planet. From the perspective of space probes orbiting Mars and the rovers resting on its surface, telescopes could be aimed outward, catching precious glimpses of the interstellar body. For a moment, it felt as though Mars itself was helping humanity study this strange traveler, offering a second window into the cosmic unknown. The mystery of 3I Atlas deepened the more it was studied. Its speed suggested an ancient journey, one that began in a star system far away, perhaps one that no longer exists. Its icy materials may hold molecules untouched for billions of years, relics of alien worlds that formed before Earth was even born. Yet so much remains hidden. We do not know the exact star it came from, nor the stories it carries locked within its frozen heart. What we do know is that it passed quietly, leaving us with wonder, questions, and the gentle reminder that the universe is far larger and far more connected than we often imagine. As it approached the inner regions of the solar system, its path brought it closer, not to Earth, but to Mars. This was a rare and almost poetic twist of fate. Mars, a planet we have studied for decades, became a vantage point for observing an object that has traveled light years across space. Telescopes in orbit and rovers on the surface allowed scientists to turn their gaze outward, catching the faint signature of 3I Atlas as it passed by. For a moment, the red planet and Earth worked together, silently aligned in the pursuit of cosmic knowledge. The closer scientists looked, the stranger it became. Its brightness fluctuated in unusual ways, hinting at a surface that was uneven, fractured, or shedding material in bursts. Some wondered if it was breaking apart, much like how cometary bodies sometimes fragment under the stress of solar radiation. Others suggested that its odd behavior was simply the result of its alien composition, materials we had never encountered before, frozen in the darkness of interstellar space for unimaginable spans of time. The shocking truth is that we know very little about where 3IATLAS came from. Its speed and trajectory suggest it was ejected long ago from another star system. Perhaps it was born in the swirling chaos of a planetary nursery, a world in formation that cast it away into the void. Or perhaps it was shattered off a larger planetesimal by a violent collision, hurled across light years until it drifted into our solar system. Its journey could have lasted billions of years, crossing silent gulfs of emptiness, never slowed, never stopped, until now. Some scientists have even suggested that interstellar visitors like this may be more common than we realize. They pass by quietly, often unseen, and only in recent years have our telescopes become powerful enough to catch them. If so, then the solar system is not as isolated as we once believed. Pieces of alien worlds may drift through our skies more often than we know, carrying with them the chemistry and history of distant suns. The presence of 3I Atlas near Mars also raises questions about the possibilities of interplanetary exchange. Could objects like this have once delivered the building blocks of life to other planets? Could molecules frozen inside carry amino acids or complex organic compounds formed in alien environments? If so, then each visitor is not just a curiosity, but a messenger, bringing hints of what is possible across the galaxy. Astronomers are careful not to overstate these mysteries. Most likely, 3I Atlas is an icy, rocky body shaped by the same natural forces that shape comets in our own system. But its rarity makes it precious. Every piece of data gathered adds to our understanding of how planetary systems form, evolve, and sometimes share fragments across interstellar distances. Each observation is like a tiny window into the larger story of the cosmos, and yet, despite what we have learned, it remains elusive. Too far for spacecraft to reach, too faint for most telescopes to study in detail, it will soon slip back into the darkness. Its trajectory ensures it will never return. Like a ghost, it will fade beyond the reach of our instruments, continuing its endless journey through the galaxy. We may never know its full story, never discover the exact star it once called home, nor the worlds it brushed past on its way here, but perhaps that is part of its gift. 31ATLAS reminds us of the vastness of space, of the billions of worlds we have not yet seen, of the unknown stories drifting silently between the stars. It reminds us that our solar system is not a closed island, but part of a greater sea where worlds and systems exchange fragments over cosmic time. As you rest and let these thoughts drift through your mind, imagine the lonely traveler continuing its path, passing by Mars, moving past the edge of our solar system, and fading into the infinite night. It has journeyed for billions of years, and it will journey for billions more. And for a brief moment, in the quiet of the cosmos, humanity saw it, wondered about it, and listened to the story it carried in silence. So close your eyes and breathe deeply. Let the vastness of space remind you of how small worries can be compared to the infinite universe. 31ATLAS will continue on, silent and eternal. And we remain here on our small blue world, watching, learning, and dreaming beneath the stars. This indicates efficient energy transfer between different molecular species, providing insights into collision rates and gas dynamics within the expanding atmosphere. The appearance of green coloration in 3E Atlas adds another data point to the growing catalog of differences between interstellar visitors and native solar system objects. 1I Oumuamua showed no clear signs of cometary activity and thus no color changes. 2 Eberos by blue and white scattered sunlight rather than molecular emission lines. 3I Atlas represents the first interstellar comet to develop the classic green coma that amateur astronomers associate with approaching periodic comets. However, the specific wavelengths and intensity of the green emission may differ subtly from those of familiar comets, potentially revealing chemical compositions unique to objects formed in other star systems. The timing of the color change creates additional observational urgency as 3I Talos approaches superior conjunction and becomes unobservable from Earth in early October. The green emission may continue evolving or could fade entirely. The peak intensity of molecular fluorescence often occurs near perihelion when solar heating reaches its maximum, but this critical period will be largely hidden from Earth-based telescopes. Spectroscopic follow-up observations attempt to identify the specific molecules responsible for the green emission, but these measurements require large telescopes and favorable observing conditions that become increasingly difficult to achieve as the comet approaches the sun's glare. Each night of clear weather becomes precious as astronomers race to characterize the emission before losing sight of their target. The green glow transformation represents more than just a visually striking development. It provides direct evidence that 3IA Atlas is undergoing fundamental chemical changes as it encounters our sun's radiation. The molecules now fusing in the comet's coma have likely remained chemically inert for millions of years, preserved in frozen silence during the object's journey between star systems. Now, for the first time since its formation, 3IA Atlas is literally lighting up as solar energy activates chemical processes that have been dormant since the comet's birth around another star. The green glow marks the awakening of alien chemistry, the first stirrings of molecular activity in materials that formed under conditions possibly unlike anything in our solar system. But observing this awakening presents challenges that push the limits. Ground-based astronomy, the challenges that will soon force researchers to rely on mechanical eyes positioned throughout the solar system to continue monitoring our transformed interstellar visitor. Part 6. Challenges in observation. Challenges in observation. The universe has a cruel sense of timing when it comes to 3I Atlas. Just as this interstellar visitor begins revealing its most intriguing secrets, the rapid brightening, the impossible coma, the alien green glow, the mechanics of orbital geometry conspire to snatch it away from Earth-based observers at the most critical moment of its journey. Professional telescopes, equipped with the most sophisticated instruments humanity can build, face the same fundamental: you cannot observe what hides behind the sun's location. As 3I Atlas continues its approach toward perihelion, its position in Earth's sky moves inexorably closer to our star's overwhelming glare, creating observational challenges that no amount of technological advancement can overcome. The James Webb Space Telescope managed to capture spectroscopic observations of 3I Atlas on August 6th using its near-infrared spectrograph, providing crucial chemical composition data during one of the few windows when the world's most advanced observatory could safely point toward the comet without risking solar damage. These observations represent some of the most detailed chemical analysis possible for an interstellar object, but they occurred before the dramatic changes of mid-September that transformed 3I Atlas from a merely unusual telescope. Contributed its own observations on July 21st, capturing high-resolution images that revealed the sunward-pointing plume structure and provided size constraints for the nucleus. However, since August, new high-resolution imagery from major space-based observatories has become sparse. The observatories that can provide the detailed analysis necessary to understand 3I Atlas's unusual behavior are the same ones most vulnerable to solar interference as the comet approaches conjunction. Ground-based observatories face their own cascade of complications. Different telescopes using different filter systems and calibration. Procedures produce brightness measurements that don't always agree with each other. This inconsistency isn't unusual in astronomy. Brightness measurement or photometry requires careful attention to atmospheric conditions, instrument calibration, and standardization procedures that can vary between observatories. The Comet Observation Database attempts to reconcile these differences by collecting brightness reports from observers. The COBS data clearly showed 3I Atlas trending brighter than predicted with measured magnitudes, but the scatter in individual measurements reflects the challenges faced by observers trying to track a rapidly changing object that defies their carefully constructed models. Amateur astronomers, often working with smaller telescopes and less sophisticated equipment, contribute valuable long-term monitoring data that professional observatories cannot always provide. However, their measurements face additional uncertainties from atmospheric turbulence, light pollution, and equipment limitations. The result is a patchwork of observations that collectively paint a picture of unusual behavior, while individually containing enough uncertainty to fuel debates about what's really happening. The SkyEv and other tracking websites compile these diverse observations into light curves that show brightness evolution over time. The sites that track 3I Atlas consistently show the same troubling trend. Measured brightness points climbing above the predicted trajectory, particularly after mid-September. Yet the precise magnitude of this deviation remains uncertain due to the inherent challenges in measuring faint, rapidly changing objects. Solar elongation, the angular separation between 3I Atlas and the Sun as seen from Earth. As this angle decreases below 30, even the most powerful telescopes struggle to separate the comet's faint light from scattered sunlight in Earth's atmosphere. Professional observatories typically cease observations when elongation drops below 20, while amateur observers may lose the object even earlier due to equipment limitations and local observing conditions. The elongation timeline creates a countdown that no human technology can extend. In early October, 3I Atlas drops below the 30th threshold that marks the beginning of serious observational difficulties. By mid-October, elongation decreases to less than 20, effectively ending routine observations from Earth's surface. This period of invisibility extends through early November, encompassing the critical weeks when solar heating reaches its maximum intensity. The irony is palpable. We're trying to watch a cosmic firefly hovering next to a floodlight, using instruments designed to detect the faintest whispers of light from the most distant galaxies. Even adaptive optic systems that can compensate for atmospheric turbulence and coronagraphies designed to block stellar light cannot overcome the fundamental physics of scattered sunlight when the comet appears too close to the sun's position in the sky. Space-based observatories theoretically possess advantages over ground-based telescopes in dealing with solar interference, but they face their own constraints. Instruments like Hubble and James Webb include protective systems that prevent them from pointing too close to the sun, automatically shutting down observations when solar angles become dangerous. These safety systems, essential for preventing catastrophic damage to billion-dollar instruments, create observation gaps precisely when they would be most valuable. The timing of 3I Atlas's conjunction period couldn't be worse for understanding its peak activity. Theoretical models predict that maximum outgassing, possible fragmentation events, and the most dramatic tail development should all occur near perihelion in late October. These are exactly the phenomena that could reveal the most about 3I Atlas's composition, structure, and origins, and they will occur largely hidden from human observation. Data processing challenges compound the observational difficulties. Images of 3 Atlas must be carefully processed to separate the comet's signal from background stars, cosmic rays, and instrumental artifacts. As the object becomes fainter relative to sky brightness during its approach to conjunction, these processing steps become increasingly critical and increasingly prone to introducing errors or artifacts. Spectroscopic observations, essential for understanding the chemical composition of the comet's coma and tail, require even more specialized conditions than simple brightness measurements. The instruments needed to disperse comet light into its component wavelengths work best with bright targets observed under dark skies. As 3I Atlas fades into solar glare, opportunities for detailed spectroscopic analysis vanish just when chemical activity may be reaching its peak. The atmospheric limitations affect different wavelengths of light in different ways. Ultraviolet emissions, crucial for detecting many molecular species in comet coms, become particularly difficult to observe as elongation decreases because Earth's atmosphere scatters blue and ultraviolet light more efficiently than red wavelengths. This scattering effect, which gives our sky its blue color, creates additional challenges for studying the chemical processes occurring within 3I Atlases. Coordination between observatories becomes essential as observing conditions deteriorate. Facilities at different latitudes and in different time zones must work together to maximize the limited observation windows available each night. Southern Hemisphere observatories may retain better viewing geometry slightly longer than their northern counterparts, creating opportunities for extended monitoring that require careful international coordination. The photometric scatter in brightness measurements reflects more than instrumental limitations. It may also indicate real variability in 3I Atlas's output. Comets can undergo rapid changes in brightness due to outgassing events, rotation effects, or structural changes in their nuclei, distinguishing between measurement uncertainty and genuine comet variability becomes increasingly difficult as signal-to-noise ratios decrease during the approach to conjunction. Weather adds another layer of uncertainty to ground-based observations. Cloud cover, atmospheric turbulence, and seasonal weather patterns at major observatories can eliminate crucial observation opportunities that will not recur. Unlike periodic comets that return predictably, 3I Atlas offers only a single passage through the inner solar system. The challenge extends beyond individual observations to the broader question of how to interpret the data that does exist. The brightness trend showing 3I Atlas exceeding predicted values could indicate enhanced outgassing, structural changes, or simply systematic errors in the theoretical models used for comparison. Resolving these questions requires the kind of detailed long-term monitoring that becomes impossible as the comet disappears into solar glare. As Earth-based astronomy reaches its limits in observing 3I Atlas, the responsibility for continued monitoring shifts to mechanical eyes positioned throughout the solar system. Spacecraft orbiting Mars, designed for entirely different missions, suddenly find themselves serving as humanity's primary observers of one of the most significant astronomical events of the decade. Part 7. The growing alarm among astronomers. Behind the measured language of scientific papers and the carefully qualified statements in astronomical bulletins, something approaching excitement and, yes, alarm ripples through the global community of comet researchers. 3I Atlas isn't behaving according to the scripts written by decades of cometry, science, and astronomers are beginning to admit in the cautious way that scientists acknowledge uncertainty that they might be witnessing something unprecedented. The brightness trend, documented by observers worldwide, represents more than statistical noise or measurement error. Multiple independent tracking systems, from the Comet Observation Database to specialized amateur networks, show the same unsettling pattern. 3I Atlas consistently outshining the predictions derived from standard cometry models. The magnitude of this deviation, several brightness levels above expected values, falls well outside the margins typically attributed to observational uncertainty. Dr. Matthew Knight, a cometry scientist who has spent his career studying how these objects behave, recently noted in an interview that the rapid brightening event observed in mid-September challenges fundamental assumptions about volatile-to-release mechanisms in comets. The speed of the change, he suggested, indicates processes operating on timescales much faster than the gradual heating models typically used to predict comet behavior. This scientific uncertainty breeds a particular type of excitement among researchers, the recognition that they might be observing phenomena that will require new theoretical frameworks to understand. Earth's Skies reporting on 3I Atlas captures this tension, describing observations that continue to surprise researchers, while acknowledging that much of what appears unusual might reflect the inherent unpredictability of objects formed in other star systems. The sunward-pointing plume structure generates its own category of scientific puzzlement. Anti-tail phenomena aren't unknown in cometry science, but the persistence and prominence of 3I Atlas's forward-directed jets push the boundaries of what existing models can easily explain. Researchers find themselves proposing increasingly exotic scenarios: unusual dust grain compositions, non-uniform nucleus rotation, exotic, volatile mixtures to account for behavior that defies textbook explanations. What everyone in the field agrees on is that 3I Atlas is demonstrating enhanced activity levels compared to typical comets at similar distances from the Sun's position. The carbon dioxide-dominated coma detected by spherics, extending to unprecedented distances, suggests outgassing rates that exceed standard predictions by significant margins. This isn't subtle deviation from theory. It's dramatic departure that demands explanation. Yet, the scientific community also grapples with what researchers call outburst bias, the tendency for comets to undergo brief periods of enhanced activity that can create false impressions of sustained, unusual behavior. Comets are notoriously prone to sudden brightness surges, followed by equally rapid returns to predicted levels. The question haunting 3I Atlas observations is whether the September brightening represents a genuine departure from normal behavior, or simply a temporary outburst that will fade as quickly as it appeared. This uncertainty becomes more troubling when considered against the backdrop of the approaching observational gap, the most critical period for understanding 3/2 Atlas's true nature, the week surrounding perihelion, when solar heating reaches maximum intensity, will occur largely hidden from Earth-based telescopes. If the comet undergoes its most dramatic transformations during this period, researchers may never understand what they witnessed in September. Dr. Carey Holt, who studies interstellar objects at the European Southern Observatory, expressed the frustration felt by many researchers. The exact moment when 3I Atlas might reveal its most significant secrets coincides with the period when Earth-based astronomy becomes least capable of observing it. The timing represents what she termed a cosmic conspiracy against scientific understanding. The debates extend beyond simple brightness measurements to fundamental questions about what 3I Atlas represents as a physical object. Its chemical composition, revealed through spectroscopic analysis, shows ratios of carbon dioxide to water vapor, unlike those typical of solar system comets. This difference could indicate formation conditions radically different from our local environment, or it might reflect chemical processing that occurred during millions of years of interstellar travel. Amateur astronomy communities have become crucial contributors to the 3I Atlas monitoring effort, providing continuous observations that professional observatories cannot always maintain. However, the scattered nature of amateur measurements introduces its own complications. Different observers using different equipment and processing techniques sometimes report brightness values that disagree by significant amounts, making it challenging to determine whether observed variations represent real changes in the comet or measurement artifacts. The European Space A's tracking efforts, coordinated through their Space Situational Awareness Program, attempt to reconcile these measurement discrepancies while maintaining continuous monitoring of 3I Atlas's trajectory and brightness evolution. Their analysis confirms the general trend toward enhanced brightness, but acknowledges the difficulties in quantifying exactly how much the comet exceeds theoretical predictions. Social media within the astronomical community reflects a mixture of scientific excitement and professional caution that characterizes response to 3I Atlas. Researchers share preliminary images and brightness measurements while carefully noting the uncertainties and limitations in their data. The tone suggests scientists are aware they're observing something potentially significant while remaining professionally skeptical about drawing premature conclusions. The green color change, documented in mid-September, adds another layer to the scientific intrigue. While diatomic carbon emission can explain the observed coloration, the timing and intensity of the green glow don't perfectly match the chemical composition indicated by earlier spectroscopic observations. This apparent discrepancy between what researchers measure chemically and what they observe visually suggests either measurement limitations or chemical processes more complex than standard models predict. Conference presentations scheduled for the American Astronomical Society's Division for Planetary Sciences meeting include multiple talks focused on 3I Atlas, observations, and theoretical modeling efforts. The abstracts reveal research groups worldwide attempting to understand not just what 3II Atlas is doing, but why existing models fail to predict its behavior accurately. The sense of urgency among researchers reflects more than scientific curiosity. It represents the recognition that opportunities to study interstellar objects remain extraordinarily rare. With only 3 confirmed interstellar visitors in human history, each object provides irreplaceable data about conditions in other star systems and the processes that govern small body formation throughout the galaxy. International collaboration has intensified as the observational window narrows. Telescopes in Chile, Hawaii, the Canary Islands, and Australia coordinate observations to maximize coverage as 3I Atlas approaches the solar conjunction period that will end routine Earth-based monitoring. Each facility contributes unique capabilities, from high-resolution imaging to specialized spectroscopic instruments, in an effort to extract maximum scientific value from the remaining observation opportunities. The professional astronomical community also grapples with public communication challenges surrounding 3I. Media reports sometimes overstate the certainty of scientific conclusions or sensationalize aspects of the comet's behavior that researchers themselves acknowledge as uncertain. Balancing public interest in this rare interstellar visitor with the inherent uncertainties of ongoing research requires careful attention to how findings are presented and interpreted. Risk assessment models developed for potentially hazardous asteroids receive new attention in the context of 3EA Atlas, not because the comet poses any danger to Earth, but because its unpredictable behavior highlights limitations in current understanding of how small bodies behave under solar heating. If researchers cannot accurately predict the behavior of 3E Atlas, questions arise about the reliability of models used to assess risks from other objects. The excitement building around 3I Atlas reflects a fundamental aspect of scientific discovery: the recognition that nature consistently produces phenomena more complex and surprising than human theories predict. As October approaches and Earth-based observations become increasingly difficult, astronomers find themselves hoping that spacecraft position throughout the solar system might capture the revelations that ground-based telescopes will be forced to miss. Part A: Mars Flyby, a golden opportunity. While Earth prepares to lose sight of 3I Atlas in the solar glare, another world positions itself for a front-row seat to one of the most significant astronomical events in recent memory. On October 3rd, 2025, Mars will host humanity's closest encounter with an interstellar visitor, offering spacecraft orbiting the red planet unprecedented opportunities to observe 3E Atlas from a vantage point Earth-based telescopes can only dream of achieving. The geometry couldn't be more fortuitous, as 3 Atlas sweeps past Mars at a distance of approximately 30 million kilometers, roughly 0.22 astronomical units. Multiple spacecraft currently operational in Martian orbit will have the opportunity to turn their instruments toward this cosmic visitor. The timing places these observations just days before superior conjunction makes Earth-based tracking impossible, creating a crucial handoff from terrestrial to space-based monitoring. The European Space A's Mars Express orbiter, launched in 2003 and still functioning far beyond its original mission timeline, carries the high-resolution stereo camera that has mapped Martian terrain in unprecedented detail for over 2 decades. While designed for planetary geology, HRSC possesses the sensitivity and resolution potentially needed to capture detailed images of 3 IALS's nucleus and inner coma structure. Dr. Colin Wilson, project scientist for the ExoMars Trace Gas Orbiter, confirmed that mission planners are evaluating opportunities for both the color and stereo surface imaging system known as CASIS, and the Nadia and occultation for Mars Discovery spectrometer Nomad to observe the interstellar visitor. These instruments, designed to study Martian atmospheric composition and surface features, might be capable of detecting chemical signatures within 3I Atlas's expanding coma. NASA's Mars Reconnaissance Orbiter presents perhaps the most intriguing possibilities for detailed observations. The higher resolution imaging science experiment HiRISE routinely captures surface details smaller than 1 meter across from its orbital altitude of roughly 300 kilometers above Mars, while 3 Atlas will pass much farther away. HiRISE's extraordinary resolution might resolve structural details of the comet's nucleus that remain invisible to Earth-based telescopes. The MAVEN spacecraft, NASA's Mars Atmosphere and Volatile Evolution mission, carries spectrographic instruments specifically designed to analyze atmospheric composition and dynamics. These capabilities could prove valuable for studying the chemical composition of 3I Atlas's coma, particularly the carbon dioxide-rich gases that dominate its spectroscopic signature. However, the observational opportunities come with significant technical challenges. All Mars orbiters were designed and optimized for studying the red planet itself, not for tracking fast-moving objects against the stellar background. The spacecraft's pointing systems, developed for observing a large nearby planet, must be reconfigured to follow a small, distant target moving at interstellar velocity. Signal strength represents the most fundamental limitation. Even at its closest approach to Mars, 3 Atlas will appear extremely faint to spacecraft instruments designed for planetary rather than deep space observations. The comet's magnitude, estimated around 12 to 14, even during its brightening phase, pushes the detection limits of most Mars orbiter cameras and spectrometers. Dr. Wilson acknowledged these limitations in recent communications with the international astronomical community. noting that while Mars-based observations of 3I Atlas are theoretically possible, the actual scientific return depends on factors, including the comet's brightness at closest approach, atmospheric conditions on Mars, and the specific geometric arrangements required for successful pointing. The advantage of Mars-based observations extends beyond simple proximity. The viewing geometry from Mars during the October 3rd flyby provides a perspective on 3 Atlas unavailable from Earth. Solar phase angles. The angle between the Sun, comet, and observer will differ significantly between Mars and Earth viewpoints, potentially revealing details of coma structure and tail geometry hidden from terrestrial telescopes. Solar wind interactions present another area where Mars orbiters might contribute unique observations. 3I Atlas's encounter with the solar wind. The stream of charged particles flowing outward from the Sun could produce phenomena detectable by the plasma and magnetic field instruments carried by several Mars missions. These interactions might reveal information about the comet's internal structure and composition through changes in its magnetic and electrical properties. The European Space A's coordination efforts for the Mars flyby observations involve unprecedented cooperation between missions designed for entirely different scientific objectives. Mars Express, originally planned for surface geology and atmospheric studies, finds itself repurposed as an interstellar object observatory. The Trace Gas Orbiter, focused on methane detection and atmospheric chemistry, must adapt its instruments for cometry spectroscopy. Timing constraints add complexity to observation planning. Mars orbiters follow predetermined schedules for routine planetary observations, communication windows with Earth, and spacecraft maintenance activities. Inserting 3IA Atlas observations into these schedules requires careful coordination to avoid conflicts with primary mission objectives while maximizing scientific opportunities. The data transmission challenges are substantial. Mars orbiters typically communicate with Earth during specific windows when both planets' orbits provide favorable geometry for radio transmission. Images and spectra of 3IA Atlas must compete with routine planetary science data for limited communication bandwidth, potentially delaying the release of observations by weeks or months. Ground-based support for Mars orbiter observations requires coordination between multiple space agencies and research institutions worldwide. The European Space Operations Center in Germany, NASA's Jet Propulsion Laboratory in California, and other facilities must work together to plan observation sequences, process incoming data, and distribute results to the international scientific community. The scientific value of successful Mars-based observations could prove transformative for understanding 3I Atlas. High-resolution imaging might resolve the nucleus size and shape with unprecedented precision, settling debates about the comet's physical dimensions and structure. Spectroscopic observations could detect molecular species invisible from Earth-based telescopes, revealing chemical compositions that preserve information about the comet's formation environment. Structural details of the coma and tail, particularly the unusual sunward-pointing plume that has puzzled researchers, might become clearer when viewed from Mars's unique perspective. The different solar phase angle could reveal whether the antitail structure results from genuine sunward ejection of material or represents a projection effect that appears different from various viewing angles. Reality requires managing expectations about what Mars orbiters can achieve. Even under optimal conditions, the scientific return from these observations will likely consist of a handful of images and spectra rather than comprehensive monitoring campaigns. The instruments were never designed for this type of observation, and their capabilities may prove insufficient to answer the fundamental questions about 3 Atlas's nature and behavior. Success depends on variables beyond human control. If 3 Atlas undergoes another brightening event before October 3rd, it might become detectable to Mars orbiter instruments that would otherwise find it too faint to observe. Conversely, if the comet fades from its current enhanced brightness levels, even the most optimistic observation scenarios might yield no useful data. The Mars flyby represents humanity's best opportunity to maintain surveillance of 3I Atlas during the critical weeks when Earth-based telescopes lose sight of this interstellar visitor. As terrestrial astronomy prepares for an imposed silence lasting through early November, the mechanical eyes orbiting Mars offer the only hope of witnessing what may prove to be the most dramatic phase of 3IA Atlas's encounter with our solar system. Whether these observations succeed or fail, they mark a new chapter in how humanity studies visitors from other star systems, demonstrating our growing capability to coordinate observations across multiple worlds. Even as the objects of our attention race past at interstellar Part 9, Superior Conjunction and Disappearance, the mathematics of celestial mechanics are utterly indifferent to human curiosity. As October progresses and 3I Atlas continues its relentless approach toward the Sun, the geometric realities of orbital motion conspire to snatch away our interstellar visitor precisely when it might reveal its most profound secrets. Superior conjunction. That period when 3I Atlas appears too close to the Sun's position in our sky for practical observation transforms one of the most significant astronomical events in recent memory into a cosmic vanishing act. The timeline unfolds with merciless precision. In early October, 3EAA Atlas drops below 30 of solar elongation. The threshold where serious observational difficulties begin for ground-based telescopes. Atmospheric scattering of sunlight creates a brightening sky background that overwhelms the faint signal from our interstellar visitor. Professional observatories, with their sophisticated adaptive optics and light-gathering power, can extend observations slightly longer than amateur telescopes. But even they face increasingly hopeless conditions. By mid-October, elongation decreases to less than 20, effectively ending routine observations from Earth's surface. The comet doesn't disappear suddenly. It fades gradually into the solar glare like a star at sunrise, becoming increasingly difficult to detect until observation becomes impossible rather than merely challenging. This gradual transition makes it difficult to pinpoint exactly when Earth loses sight of 3I Atlas, but the practical result remains the same. Our primary window into the comet's behavior closes just as solar heating approaches its maximum intensity. The conjunction period extends through early November, encompassing roughly 4 to 5 weeks when 3-2 Atlas remains effectively invisible from Earth. This isn't simply an inconvenient gap in observations. It represents the complete loss of our ability to monitor the comet during what theoretical models predict should be its most active period. Peak outgassing, maximum tail development, possible fragmentation events, and other dramatic phenomena could all occur hidden from human view. The cruel irony becomes more apparent when considered against the backdrop of 3I Atlas's recent behavior. The rapid brightening observed in September, the unusual antitail structure, and the distinctive green coloration all suggest an object undergoing fundamental changes as it encounters our sun's radiation. Logic dictates that these transformations should intensify as solar heating increases, potentially reaching spectacular levels near perihelion in late October. Yet, perihelion occurs almost exactly at the midpoint of the conjunction period when 3I Atlas appears. Closest to the Sun in Earth's sky, and observation becomes most impossible. The timing couldn't be worse for understanding what this interstellar visitor truly becomes when subjected to maximum solar influence. It's as if the universe deliberately arranged for the most interesting part of the show to occur behind a drawn curtain. The physics behind superior conjunction involve no conspiracy against scientific discovery, merely the geometric consequences of observing from a planet orbiting the same star as our target. As 3 Atlas approaches perihelion, its apparent position in the sky necessarily approaches the Sun's location. The angular separation decreases steadily until the comet appears to pass behind our star, creating observational conditions that no amount of technological sophistication can overcome. Professional astronomers face this limitation with frustrating regularity. When studying objects that approach close to the Sun's location, solar observing satellites like the Solar and Heliospheric Observatory, SOHO, can sometimes track comets during conjunction periods using coronagraphs that block the Sun's direct light. However, 3 Atlas's trajectory doesn't pass close enough to the Sun for detection by these specialized instruments, which typically observe objects within a few solar radii of our star. The conjunction gap creates unprecedented challenges for a scientific community accustomed to continuous monitoring capabilities. Modern astronomy relies heavily on long-term observation campaigns that track objects through complete cycles of activity. Comets, in particular, require extended monitoring to distinguish between temporary outburst events and sustained changes in behavior. The forced observational hiatus during 3I Atlas's most critical period eliminates the possibility of this type of comprehensive analysis. Spacecraft positioned throughout the solar system offer limited alternatives to ground-based observations, but their capabilities remain constrained by original mission designs focused on planetary rather than cometary studies. The Mars orbiters discussed earlier provide the most promising near-term opportunities, but their observations will be brief snapshots rather than the continuous monitoring needed to fully understand 3I Atlas's evolution. The European Space A's Bay Colombo mission, currently en route to Mercury, follows a trajectory that might provide occasional opportunities to observe 3I Atlas from a different vantage point than Earth. However, the spacecraft's instruments are optimized for Mercury studies, and the geometric requirements for comet observations may not align favorably with mission operational constraints. NASA's Parker Solar Probe, designed to study the Sun's corona and solar wind, operates in the inner solar system, where it might theoretically encounter 3I Atlas's tail or coma material. However, the probe's highly elliptical orbit and focus on solar rather than cometary phenomena limit its utility for systematic comet observations. The conjunction period also creates challenges for theoretical modeling efforts attempting to predict 3I Atlas's behavior. Computer simulations of comet activity rely on observational data to calibrate their predictions and validate their accuracy. The 4 to 5 W gap in observations eliminates crucial data points that modelers need to refine their understanding of how this interstellar responds to solar heating. When Earth-based observations resume in November or early December, 3I Atlas will likely have changed dramatically from the object astronomers studied in September. The comet may have brightened further, possibly developing spectacular tail structures visible through amateur telescopes. Alternatively, it might have faded significantly if volatile materials became depleted during the unobserved perihelion passage. More dramatically, 3I Atlas might have fragmented into multiple pieces during its closest approach to the Sun's position. Comet fragmentation isn't uncommon near perihelion, where tidal forces and thermal stresses can overcome the weak gravitational binding holding nucleus materials together. If fragmentation occurs during conjunction, Earth-based observers will face the challenging task of identifying and tracking multiple objects when observations become possible again. The resumption of observations in late November or December will require careful planning and coordination among observatories worldwide. 3I Atlas will emerge from conjunction in a different region of the sky, requiring telescopes to locate and reacquire the comet after weeks of invisibility. The object's brightness, position, and appearance may have changed sufficiently to complicate identification and tracking efforts. Public interest in 3I Atlas faces its own conjunction-related challenges. Media coverage of astronomical events typically relies on dramatic images and continuous updates to maintain audience engagement. The forced silence during the conjunction period eliminates the steady stream of new observations that sustain public attention, potentially reducing interest just as the comet experiences its most significant transformations. Educational opportunities also suffer during the conjunction gap. Schools and amateur astronomy groups often use bright comets as tools for teaching about solar system dynamics and observational techniques. 3I Atlas's disappearance into solar glare eliminates these opportunities during what might be the comet's most photogenic period, when tail development and nuclear activity could provide the most visually spectacular educational content. The conjunction period serves as a reminder of astronomy's fundamental limitations despite centuries of technological advancement. Humans remain bound to their home planet for most astronomical observations, subject to the geometric constraints imposed by Earth's position relative to observed objects and the Sun's. Even our most sophisticated space-based telescopes cannot completely overcome these limitations when objects approach too close to our star's position. As 3 Atlas vanishes into solar glare, the astronomical community prepares for a period of speculation and theoretical modeling based on incomplete data. The question isn't whether the comet will change during its hidden passage. It's whether those changes will be comprehensible when observations resume, or whether the conjunction gap will leave permanent mysteries about what happened during the most critical phase of this interstellar visitor's encounter with our sun's orbit. Part 10. Perihelion Expectations. Deep within the solar glare that blinds Earth's telescopes, 3IA Atlas prepares for its appointment with destiny. On October 29th to 30th, 2025, this interstellar wanderer will reach perihelion, its closest approach to the Sun, at approximately 1.36 to 1.4 astronomical units. Hidden from human observation, the comet will experience solar radiation intensities unlike anything in its multi-million-year journey between star systems, potentially undergoing transformations that could redefine our understanding of interstellar objects. The speed evolution alone tells a story of cosmic violence. Currently racing through space at tens of kilometers, 3I Atlas will reach its maximum velocity near perihelion, potentially hitting 68 kilometers per second, or approximately 152,000 miles per hour. To appreciate this extraordinary speed, consider that Earth maintains its stable orbit around the Sun at roughly 30 kilometers per second. 3I Atlas will be moving more than twice as fast as our entire planet, carrying kinetic energy accumulated during its epic journey across the galaxy. Physics predicts that perihelion will trigger the most dramatic phase of 3I Atlas's solar system encounter. As solar heating reaches maximum intensity, the temperature of the comet's nucleus will soar, potentially activating volatile compounds that have remained stable throughout its interstellar voyage. Water, ice, carbon dioxide, carbon monoxide, and more exotic frozen gases could all begin sublimating simultaneously, creating an explosive expansion of the coma that might dwarf the already unprecedented dimensions observed in September. The increased outgassing could produce spectacular dust jets erupting from discrete locations on the nuclear surface. These jets, formed when subsurface volatile deposits find pathways to escape, can create fountain-like structures extending thousands of kilometers into space. The sunward-pointing antitail that has puzzled observers might intensify dramatically, or entirely new tail structures could emerge as different volatile compounds begin contributing to the coma for the first time. Theoretical models suggest that 3I Atlas's carbon dioxide-rich composition might produce perihelion behavior. Unlike that of typical solar system comets, carbon dioxide sublimes more readily than water ice at the temperatures expected near potentially creating gas production rates that exceed those of water-dominated comets by significant factors. This enhanced activity could manifest as rapid changes in brightness, coma size. The possibility of fragmentation looms over perihelion predictions like a shadow of uncertainty. Comets represent some of the most fragile objects in the solar system, held together by weak gravitational forces and the structural integrity of their icy matrices. The thermal stresses induced by intense solar heating, combined with the mechanical forces generated by explosive outgassing, can overcome these binding forces and tear nuclei apart. Fragmentation events can unfold with dramatic suddenness. A comet that appears stable during its approach to perihelion can split into multiple pieces within hours as thermal gradients create structural weaknesses or gas pressure eruptions. Excavate material from the nucleus interior. If 3I Atlas undergoes fragmentation, Earth-based observers will face the complex task of identifying and tracking multiple objects when observations resume in November. The historical precedent for comet fragmentation near perihelion includes spectacular examples like Comet Shoemaker Levy 9, which broke apart under Jupiter's tidal forces before impacting the planet in 1994. More recently, Comet is disintegrated during its extremely close approach to the Sun in 2013, creating a debris cloud that dispersed rapidly as it moved away from perihelion. However, fragmentation isn't inevitable. The structural integrity of 3I Atlas depends on factors including nucleus composition, internal porosity, rotation rate, and the specific thermal stresses generated by its unique, volatile mixture. Interstellar objects might possess structural characteristics that differ significantly from solar system comets, potentially making them more or less susceptible to thermal disruption. The speed at which 3IA Atlas passes through perihelion also influences fragmentation risk. Unlike some comets that linger near their closest solar approach, 3EA Atlas will sweep past perihelion relatively quickly due to its hyperbolic trajectory. This rapid passage limits the duration of peak heating, potentially reducing the cumulative thermal stress experienced by the nucleus. If 3I Atlas survives perihelion intact, the post-perihelion period should reveal an object transformed by its encounter with intense solar radiation. The coma might expand to even larger dimensions as peak gas production rates distribute material across unprecedented volumes of space. New chemical species liberated from subsurface deposits by deep heating could appear in spectroscopic observations for the first time. Color changes beyond the green emission already observed might develop as different molecular species begin fluorescing under solar ultraviolet radiation. Complex organic compounds, if present in the nucleus, could break down into simpler fragments that emit light at characteristic wavelengths, potentially creating a rainbow of emissions across the visible spectrum. The antitail phenomenon that has characterized 3I Atlas observations might evolve dramatically near perihelion. Enhanced dust production could create multiple tail structures pointing in different directions as particles of various sizes respond differently to solar radiation pressure. The resulting geometry could provide crucial information about the nucleus rotation rate, surface composition, and internal structure. Dust grain analysis becomes particularly important during the perihelion period. The size, distribution, and composition of particles ejected from the nucleus reflect the internal structure and formation conditions of the original object. Large grains might indicate a loosely consolidated nucleus with significant void spaces, while fine dust could suggest a more compact structure or specific chemical compositions that favor the production of small particles. The magnetic and plasma environment near perihelion adds another layer of complexity to 3I Atlas's behavior. The solar wind-charged particles streaming outward from the Sun interacts with the ionized gases in the comet's coma to create complex electromagnetic phenomena. These interactions can accelerate particles to high velocities, create visible glows in the coma, and influence the development of plasma tails that extend millions of km behind the nucleus. Temperature measurements during perihelion, if obtainable through spacecraft observations, could provide fundamental insights into 3I laces, thermal properties, and internal structure. Different volatile compounds sublimate at specific temperatures, creating a chemical thermometer that reveals the heating progression within the nucleus. A solar radiation penetrates its surface layers. The aftermath of perihelion will depend critically on how much volatile material 3I Atlas contains and how efficiently that material can escape through the nuclear surface. Objects with large volatile reserves might continue showing enhanced activity for weeks or months after while those with limited volatile content could fade rapidly as their surface layers become depleted. Gravitational perturbations from the sun's intense gravitational field near could also affect 3I Atlas's future trajectory, while the comet will definitely continue outward on its hyperbolic path. Small changes in velocity could alter the timing and geometry of future encounters with outer solar system planets, particularly Jupiter. In 2026, the perihelion passage represents the climax of 3I Atlas's solar system encounter, the moment when billions of years of interstellar evolution meet the intense radiation environment surrounding our star. Whether this meeting produces spectacular displays of cosmic pyrotechnics or quiet, structural transformations hidden within an expanding coma, the perihelion will fundamentally alter 3I Atlas from the object that entered our solar system into something new and unprecedented. The question that will haunt astronomers through the conjunction period is whether 3I Atlas will emerge from its hidden perihelion passage, recognizable as the same object that captivated observers in September, or as something entirely transformed by its encounter with our sun's most intense radiation. The answer lies hidden in solar glare, awaiting the patient geometry of orbital mechanics to reveal what perihelion has wrought. Part 11. Comparisons to past interstellar objects. To understand the significance of 3I Atlas and its bizarre behavior, we must look backward through the brief but revolutionary history of confirmed interstellar visitors. Only 2 objects before our eye, the current visitor, have been definitively identified as originating beyond our solar system, and each has rewritten astronomical textbooks in its own unique way. The story they tell together is one of cosmic diversity that challenges every assumption about how these wandering messengers from other star systems should behave. 1. Oumuamua arrived first discovered on October 19, 2017 by the Panoramic Survey Telescope and Rapid Response System, PAN-STARRS, in Hawaii. Initially classified as an asteroid due to its lack of visible coma, Oumuamua quickly proved that interstellar objects would not conform to Earth-based expectations. Its highly elongated shape, roughly 400 meters long and 40 meters wide, resembled no asteroid or comet previously observed in our solar system. More puzzling still, Oumuamua exhibited non-gravitational acceleration as it moved away from the Sun, speeding up in ways that couldn't be explained by gravitational forces alone. This mysterious acceleration sparked debates that continue today. Was it outgassing from hidden volatile deposits, solar radiation pressure acting on an unusually shaped object, or something more exotic that pushed the boundaries of conventional physics? The absence of a detectable coma around Umu, a more contradicted expectations for objects containing the volatile ices typical of comets. Yet something was clearly acting on the object to produce the observed acceleration. The resolution, if it can be called that, involved invoking outgassing so minimal that it remained below detection thresholds while still generating enough force to alter Umyon's trajectory. 2I Boris, discovered on August 30th, 2019 by amateur astronomer Gennady Boris in Crimea, presented a completely different personality. Unlike its predecessors' enigmatic behavior, Boris appeared refreshingly normal at first glance. A classic comet, complete with fuzzy coma and developing tail structures that matched theoretical expectations for objects heated by solar radiation. However, detailed analysis revealed that Borisov's apparent normally masked chemical compositions, unlike anything found in native solar system comets. Spectroscopic observations showed carbon monoxide concentrations significantly higher than those typical of local comets, suggesting formation conditions in a protoplanetary disk with different temperature and chemical gradients than our own solar nebula. The dust-to-gas ratio in Borisov's coma also differed from solar system norms, indicating either different formation processes or evolutionary changes that occurred during its interstellar journey. These subtle but significant chemical differences provided the first direct evidence that other star systems produce comets with compositions reflecting their unique formation environments. Now 3I Atlas enters this exclusive club with characteristics that make both of its predecessors seem mundane by comparison. The carbon dioxide-rich coma detected by Spherics and confirmed through follow-up observations represents the most extreme compositional departure from solar system norms, yet observed in an interstellar visitor. The CO2 to water vapor ratio suggested by James Webb Space Telescope analysis indicates formation conditions even more exotic than those that produced Boris, the sunward pointing anti-tail structure of 3 Atlas has no parallel in previous interstellar object observations. While Umaam showed no tail structures due to its apparent lack of significant outgassing, and Boris displayed conventional comet tails streaming away from the sun, Atlas creates geometry that defies basic principles of comet physics as understood through centuries of observation. The rapid brightening trend documented in September 2025 adds another unique characteristic to 3I Atlas's growing list of anomalies. Neither Oumuamua, nor Boris exhibited such dramatic short-term brightness variations, suggesting that 3I Atlas undergoes processes, whether outgassing events, structural changes, or surface evolution, operating on timescales faster than those typical of previously studied interstellar objects. Size comparisons reveal interesting patterns in the interstellar visitor population. OM's dimensions, estimated at roughly 400 by 40 by 40 m, significantly larger than typical small asteroids, but smaller than most active comet nuclei. Borisov's nucleus diameter, estimated at approximately 1 kilometer, fell within the normal range for solar system comets. 3I Atlas presents size estimation challenges that reflect the uncertainty surrounding its fundamental nature. Hubble Space Telescope observations suggest a nucleus diameter somewhere between 0.32 and 5.6 kilometers, a range that encompasses both small and moderately large comet nuclei. The uncertainty arises from difficulties in separating the nucleus from its extensive coma, itself a unique characteristic that distinguishes 3IA Atlas from its interstellar predecessors. Chemical analysis capabilities have evolved significantly between the discovery of each interstellar visitor, allowing progressively more detailed composition studies. MMU's brief visibility period and lack of significant outgassing, limited chemical analysis to surface reflection properties, and rough density estimates. Borisov's more conventional comet behavior enabled spectroscopic detection of water vapor, carbon monoxide, and various other molecular species, typical of comet comas. 3I Atlas benefits from the most advanced observational capabilities yet applied to an interstellar object. James Webb Space Telescope's infrared spectroscopy, Hubble's high-resolution imaging, and ground-based observatories equipped with next-generation spectrographs provide unprecedented detail about chemical composition, physical structure, and temporal evolution. The orbital, the characteristics of each interstellar visitor also tell their own stories about galactic dynamics and the processes that eject objects from their birth star systems. Umu Oumuamua approached the solar system from the direction of the star Vega, though its journey time exceeded Vega's age, indicating a more complex galactic trajectory. Its hyperbolic excess velocity, the speed it would retain after escaping solar gravitational influence, measured approximately 26 kilometers per second. Trajectory suggested origin from a region of space containing young hot stars in the constellation Cassiopeia, with a hyperbolic excess velocity of approximately 32 kilometers per second. Higher velocity indicated either ejection from a more massive star system or acceleration through gravitational interactions during its interstellar journey. 3IA Atlas carries the highest hyperbolic excess velocity yet measured for an interstellar object, estimated at approximately 39 kilometers per second. Extreme velocity suggests either formation around a particularly massive star or acceleration through multiple gravitational encounters during its journey through the galaxy. The velocity also influences the object's behavior near perihelion, as higher speeds reduce the time available for solar heating to penetrate deep into the nucleus interior. The discovery intervals between interstellar visitors provide insights into their population in the galaxy. The 2-year gap between Oumuamua and Borisov, followed by the 6-year interval before 3I Atlas, suggests that such objects pass through the inner solar system regularly but remain difficult to detect due to their small sizes and brief visibility periods. Statistical analysis of the 3 confirmed interstellar objects indicates that each represents a different type of small body formation process, suggesting enormous diversity in how other star systems produce and eject comets and asteroids rather than converging toward typical characteristics. Each new interstellar visitor has expanded the range of possible behaviors and compositions. The unique characteristics of 3I Atlas, the unprecedented coma size, antitail structure, chemical composition, and brightness evolution suggest that interstellar object diversity encompasses phenomena not yet imagined by theoretical models based on solar system experience. Each visitor teaches new lessons about planetary formation processes throughout the galaxy, while simultaneously raising new questions about what other types of interstellar objects await discovery. As 3 Atlas continues its hidden passage through perihelion, astronomers can only speculate about whether its post-conjunction appearance will add new entries to the growing catalog of interstellar object peculiarities. The pattern established by Oumuamua and Boris suggests that 3I Atlas will continue surprising researchers with behaviors that challenge fundamental assumptions about small body physics. The lesson emerging from all 3 interstellar visitors is that the galaxy produces small bodies through processes far more diverse and complex than those operating in our local solar system. Each object carries chemical and physical signatures of formation to saw environments that differ dramatically from our own cosmic neighborhood, providing direct samples of planetary system evolution occurring throughout the Milky Way. Part 12. Scientific Unknowns and Active Debates. The scientific community's response to 3I Atlas resembles a detective story where crucial evidence remains locked away, forcing researchers to construct theories from incomplete clues, while the most important information lies hidden behind solar glare. Multiple competing hypotheses attempt to explain the comet's unusual behavior, but each explanation raises new questions that may remain unanswered until or unless post-conjunction observations provide the missing pieces of this interstellar puzzle. The nucleus, size, and shape controversy illustrates the fundamental challenges facing 3I Atlas researchers. Hubble Space Telescope observations have narrowed the size estimate to somewhere between 0.32 and 5.6 kilometers in diameter. But this broad range reflects the difficulty of separating the solid nucleus from its extensive coma. The uncertainty matters because size directly affects calculations of mass, density, surface area available for outgassing, and structural stability during the intense heating of perihelion. Different measurement techniques produce conflicting results. Thermal modeling based on infrared observations suggests a smaller nucleus with high albedo, a reflective surface that efficiently scatters sunlight. Visible light analysis indicates a larger, darker nucleus that absorbs more solar radiation. The discrepancy could result from surface composition variations, measurement uncertainties, or fundamental misunderstandings about how 3I Atlas responds to solar heating. Compositional analysis faces its own set of contradictions. James Webb Space Telescope spectroscopy clearly identifies carbon dioxide as the dominant volatile species in 3 Atlas's coma, with CO2 concentrations exceeding those of water vapor by significant margins. This composition differs dramatically from solar system comets, where water typically dominates volatile inventories. However, the carbon dioxide dominance creates theoretical problems for explaining other observed characteristics. The green coloration that developed in September typically indicates diatomic carbon emission, but CO2-rich outgaing doesn't naturally produce the carbon-bearing molecules responsible for green fluorescence either. The spectroscopic analysis missed important chemical constituents, or the green coloration results from processes more complex than simple molecular fluorescence. Ground-based spectroscopic observations from the Very Large Telescope and the major observatories have detected additional molecular species, including cyanide compounds and various organic molecules. These detections hint at chemical complexity beyond the simple CO2 dominance indicated by space-based observations, suggesting that 3 Atlas contains a diverse inventory of both simple and complex carbon-bearing compounds. The anti-tail structure presents perhaps the most perplexing observational puzzle. Conventional comet physics dictates that solar radiation pressure should push gas and dust away from the sun, creating tails that point radially outward from the solar direction. 3 Atlas appears to violate this fundamental principle by ejecting material that forms structures pointing toward the sun rather than away from it. Dr. Quito and Dr. Liu's recent theoretical analysis, currently undergoing peer review, proposes that the antitail results from unusual dust grain size distributions combined with specific ejection geometries from the nuclear surface. Their model suggests that large dust particles ejected sunward with sufficient initial velocity can overcome solar radiation pressure to create the observed forward-pointing structures. However, competing models invoke different physical mechanisms. Some researchers proposed that electromagnetic effects, interactions between charged dust particles, and solar magnetic fields could redirect material in unexpected directions. Others suggest that 3 Atlas's rotation state creates temperature asymmetries that concentrate outgassing in specific directions regardless of solar radiation pressure. The rotation period of 3I Atlas remains unknown despite months of observation attempts. Light curve analysis, which measures brightness variations caused by an irregularly shaped nucleus rotating in sunlight, has failed to reveal clear periodic signals. This absence of detectable rotation signatures could indicate either very slow rotation, a nearly spherical shape, or rotational complexity that obscures simple periodic variations. Rotation state affects multiple aspects of comet behavior. Rapidly spinning objects experience centrifugal forces that can influence outgassing patterns and structural stability. Slowly rotating comets develop temperature differences between day and night sides that concentrate volatile release in heated regions. The unknown rotation characteristics of 3I Atlas complicate efforts to model its thermal evolution and predict future behavior. The brightness evolution documented in September presents its own interpretive challenges. Multiple observation networks confirmed that 3-2 Atlas became significantly brighter than theoretical predictions, but the magnitude of this deviation remains debated. Some observers report brightness increases equivalent to several magnitude levels, while others suggest more modest enhancements that fall within the normal range of comet variability. The discrepancies arise partly from measurement difficulties. 3I Atlas remains near the detection limits of most telescopes, making accurate photometry challenging even under optimal conditions. Different observers use different comparison stars, filter systems, and reduction procedures that can introduce systematic errors into brightness measurements. More fundamentally, the lack of baseline observations complicates brightness trend analysis. Unlike periodic comets that have been observed through multiple apparitions, 3IA atlas represents a single opportunity target with no historical data for comparison. Researchers must rely on theoretical models based on solar system comets to establish expected behavior, but these models may not apply to objects formed in other star systems. Origin studies attempt to trace 3I Atlas's trajectory backward through the galaxy to identify its probable birth location. Current kinematic analysis suggests the comet originated somewhere within the Milky Way's thin disk, the flat staric region where most current star formation occurs. However, the uncertainties in measured position and velocity propagate backward through time, creating increasingly large error ellipses that encompass multiple possible source regions. The galactic origin question has implications for understanding 3I Atlas's composition and age. Objects ejected from young star systems might retain different chemical signatures than those originating from older, more evolved stellar environments. The carbon dioxide dominance could reflect formation in a protoplanetary disk with temperature and chemical gradients. Unlike those that produce solar system objects, structural stability represents another area of active debate. The extensive coma and antitail structure suggest vigorous outgassing that could indicate either a volatile-rich nucleus or one undergoing structural disruption. Some researchers propose that 3I Atlas represents a loosely bound collection of smaller objects. Alternative models treat 3I Atlas as a monolithic object with unusual surface properties or internal structure that produces the observed outgassing patterns. The distinction matters for predicting behavior near perihelion, where thermal stresses and tidal forces reach maximum intensity. The 2 astronomical unit switch-in moment observed in early September remains poorly understood. The sudden increase in activity as 3I Atlas crossed this distance from the Sun could indicate the activation of specific volatile compounds that sublimate at particular temperatures. Alternatively, it might reflect structural changes in the nucleus that exposed previously buried volatile deposits to solar heating. Different volatile species sublimate at different distances from the Sun, creating a natural sequence of activation. As comets approach perihelion, water ice begins significant outgassing around 3 astronomical units, while carbon dioxide can remain active at much greater distances. The specific behavior of 3I Atlas suggests a complex mixture of volatile compounds with activation temperatures that don't match solar system comet experience. The observational gap during conjunction creates additional uncertainty about which theoretical models best explain 3I Atlas's behavior. The most critical tests of competing hypotheses: how the comet responds to maximum solar heating, where the fragmentation occurs, how outgaing patterns evolve, will occur largely hidden from Earth-based observation. When 3I Atlas emerges from conjunction in late November, researchers will face the challenge of interpreting observations of an object that may have changed dramatically during its invisible perihelion passage. The post-conjunction appearance could either validate current theoretical models or introduce new puzzles that require entirely different explanations. The scientific debates surrounding 3I Atlas reflect the broader challenge of understanding phenomena that occur only rarely and under conditions that push observational capabilities to their limits. Each measurement carries uncertainties. Each model makes assumptions, and each interpretation must account for the possibility that interstellar objects operate according to physical principles not yet discovered through solar system experience. Part 13. Natural explanations. Before venturing into the realm of truly speculative possibilities, the comet may be strange beyond current understanding, but it likely remains within the boundaries of known physics, albeit operating under conditions so extreme that they've never been observed before in human experience. The carbon dioxide dominance detected in 3I Atlas's coma provides the first clue to understanding its alien nature through conventional cometry science. This composition suggests formation in a region of its birth star system where temperatures remained low enough for CO2 to condense into solid ice, while water existed primarily as vapor. Such conditions typically occur beyond what astronomers call the carbon dioxide snowline, the distance from a star where carbon dioxide can freeze out of the gaseous phase. In our solar system, the CO2 snowline lies much farther from the Sun than the regions where most comets form. This explains why solar system comets show water as their primary volatile component, with carbon dioxide playing only a secondary role. However, other star systems could have different temperature profiles, stellar luminosities, or chemical compositions that place the CO2 snowline at distances where significant comet formation occurs. A star cooler than our Sun would push the carbon dioxide snowline closer to the star, allowing CO2-rich comets. Alternatively, a star with different chemical composition could produce protoplanetary disks where carbon dioxide formation is favored over water ice. Formation regardless of temperature. The formation environment hypothesis explains not only 3's unusual chemistry, but also its enhanced outgaing behavior. Carbon dioxide sublimes more readily than water ice at the same temperature, potentially producing gas release rates that exceed those of water-dominated comets by significant factors. This enhanced volatility could account for the rapid brightening observed in September and the unprecedented size of the coma detected by. However, the CO2-rich composition alone cannot explain the sunward pointing antitail that has puzzled observers since the first detailed images appeared. This is where dusty plasma physics enters the equation, introducing processes that operate at the intersection of solid mechanics, gas dynamics, and electromagnetic phenomena. When solar ultraviolet radiation ionizes gases in a comet's coma, it creates a plasma, a soup of electrically charged particles that responds to both gravitational forces and electromagnetic fields. Ionized material interacts with charged dust grains in complex ways that can produce self-organizing structures unlike anything predicted by simple gravitational and radiation pressure models. Charged dust particles can form streams, filaments, and even spiral structures when influenced by magnetic fields carried in the solar wind. Under specific conditions, these electromagnetic effects might overcome radiation pressure, allowing material to flow in directions that appear to violate basic comet physics. The result could be antitail structures that point toward the Sun, while conventional tails stream away from it. The plasma physics explanation gains credibility when considering 3I Atlas's enhanced outgassing rates. Higher gas densities create more opportunities for ionization and charge exchange processes that could amplify electromagnetic effects. The unusual chemical composition might also influence plasma formation through molecular species that ionize more readily, or at different rates than those typical of solar system comets. Rotation state offers another avenue for explaining 3I atlases' anomalous behavior through conventional physics applied to extreme conditions. A nucleus with very slow rotation could develop temperature differences between its day and night sides that concentrate outgassing in specific regions rather than distributing it uniformly across the surface. If 3 Atlas rotates slowly enough that its day side reaches significantly higher temperatures than solar system comets experience, thermal expansion and gas pressure could create jets of material ejected with velocities high enough to overcome solar radiation pressure in the sunward direction. The result would be preferential ejection toward the sun from the hottest regions of the nuclear surface. The slow rotation hypothesis requires explaining why 3A Atlas would rotate differently from typical comets. Interstellar objects experience different evolutionary processes during their journeys between star systems. Collisions with interstellar dust particles, gravitational talks from passing stars, or magnetic field interactions could all alter rotation states in ways that don't occur for objects remaining within single stellar systems. The green coloration that appeared in September presents its own natural explanation challenges. Diatomic carbon typically produces green emission in comet comas, but initial spectroscopic observations showed relatively little evidence for carbon-bearing molecules other than carbon dioxide. However, the threshold hypothesis suggests that C2 release became significant only when 3-day Atlas crossed a specific temperature or solar radiation threshold near the 2 astronomical unit distance. This threshold effect could result from carbon dioxide photodissociation, the breakdown of CO2 molecules by solar ultraviolet radiation into carbon monoxide and atomic oxygen. Further photodissociation of carbon monoxide could produce the carbon atoms necessary for diatomic carbon formation. The process requires specific radiation conditions and molecular densities that might not have been present during 3Desis's initial observations, but developed as the comet approached closer to the Sun's orbit. Alternative carbon chemistry involves complex organic molecules that could exist in trace quantities within the nucleus but produce detectable emission only under specific excitation conditions. Polycyclic aromatic hydrocarbons, amino acids, or other organic compounds could break down under intense solar radiation to produce carbon-bearing fragments that fuse at green wavelengths. Surface composition variations offer another natural explanation for 3I unusual behavior rather than a uniform nucleus composition. The object might contain discrete regions with different chemical makeups, some rich in carbon dioxide, others containing water ice, and still others harboring complex organic materials. As 3I approaches the Sun and different regions of its surface experience heating for the first time, these chemical variations could produce outgassing patterns that change over time. The initial CO2 dominance might reflect early activation of the most volatile surface deposits, while later heating could expose subsurface materials with different compositions. Porosity and internal structure also influence comet behavior in ways that could explain 3. Illus's anomalous characteristics. A highly porous nucleus, essentially a loose collection of ice and dust held together by weak forces, could allow deep penetration of solar heating that activates subsurface volatile deposits, normally insulated from external temperature changes. The enhanced paucity hypothesis explains both the extensive coma and the rapid brightness changes. Deeper heating activates larger volumes of volatile material than typically occurs in more compact comet nuclei, creating gas production rates that exceed model predictions based on surface heating alone. Interstellar processing during 3 Atlas's journey between star systems might have created structural modifications not experienced by solar system objects. Cosmic ray bombardment, interstellar dust impacts, or thermal cycling during passages through different radiation environments could all alter nucleus properties in ways that influence behavior when the object finally encounters intense stellar radiation. The most likely explanation for 3 Atlas's extraordinary behavior involves combinations of these natural processes operating simultaneously. CO2-rich composition drives enhanced outgassing. Plasma physics creates antitail structures. Slow rotation concentrates activity in specific regions, and complex chemistry produces the observed color changes, while each individual process remains within well-understood physics. Their interaction under the extreme conditions of an interstellar comet encounter might produce phenomena that appear impossible when considered through the lens of solar system comet experience. 3. I-Atlas could represent a profoundly weird comet rather than something fundamentally alien, but that weirdness makes it precisely the type of object that could revolutionize understanding of small body physics throughout the galaxy. Part 14. Exotic and fringe theories. Now we venture into territory where science fiction meets speculative possibility, where the boundaries between natural phenomena and truly extraordinary explanations begin to blur. While no credible evidence supports these exotic interpretations of 3I Atlas's behavior, the comet's unprecedented characteristics invite the kind of speculation that has accompanied every unexplained astronomical phenomenon throughout human history. These ideas exist not as serious scientific hypotheses, but as thought experiments that illuminate just how strange our interstellar visitor truly island. The alien technology beacon hypothesis represents perhaps the most persistent, exotic explanation for unusual astronomical objects. Ever since one Moim Emoy's discovery sparked debates about artificial origins, each new interstellar visitor inevitably generates speculation about possible technological signatures. 3. I-Atlas's rapid brightening, unusual antitail structure. An enhanced coma could theoretically represent activation sequences of some form of automated probe designed to respond to stellar radiation environments. The beacon scenario imagines 3I Atlas as a dormant technological artifact that remained inactive during its long journey between star systems, preserving power and structural integrity until encountering conditions that trigger preset activation protocols. The brightening event in September could mark the moment when solar radiation reached sufficient intensity to power dormant systems, while the antitail structure might represent directed energy emissions or material ejections, serving some technological purpose. However, this technological interpretation faces immediate challenges when confronted with observational evidence. The spectroscopic signatures detected by James Webb Space Telescope and ground-based observatories show clear evidence for standard volatile compounds, carbon dioxide, water vapor, and organic molecules that match expectations for natural comet outgang. No unusual isotopic ratios, artificial materials, or energy signatures characteristic of advanced technology have been detected. The quasi-living plasma hypothesis ventures even further into speculative territory, drawing on research into complex plasma behaviors that can exhibit seemingly organized patterns under specific conditions. Laboratory experiments have demonstrated that dusty plasmas, mixtures of charged particles, and microscopic solid grains can self-organize into structures that exhibit properties reminiscent of biological systems. These plasma formations can reproduce, evolve, and respond to environmental changes in ways that superficially resemble living organisms. Some researchers have speculated that such complex plasma systems might arise naturally in space environments, potentially developing behaviors that mimic primitive life forms. 3. I-Atlas's unusual outgassing patterns, antitail structures, and responsive brightening could theoretically represent manifestations of such plasma-based phenomena. The living plasma concept suggests that interstellar space might harbor forms of organization that operate according to physical principles completely different from carbon-based biology. These hypothetical entities might remain dormant during interstellar travel, but become active when encountering the electromagnetic environment surrounding stars, producing observable effects that mimic but don't truly represent biological processes. Yet, this explanation requires invoking physical mechanisms that remain purely theoretical. While dusty plasmas can indeed form complex structures under laboratory conditions, scaling these phenomena to comet-sized objects operating in the solar wind environment requires extrapolations far beyond current scientific understanding. No observational evidence suggests that 3I Atlas exhibits the type of electromagnetic signatures expected from large-scale plasma organization. The purposeful scout narrative transforms 3I Atlas into an active reconnaissance mission from another star system, complete with programmed behaviors designed to study our solar system during its passage through the inner regions. This scenario imagines the comet's unusual characteristics as intentional features. The extensive coma might provide sensor capability or communication range, while the antitail structure could represent data transmission systems aimed at distant receivers. The Scout hypothesis suggests that 3I at brightening represents not random outgassing, but controlled activation of observation and communication systems as the object approaches its primary mission targets. The timing of peak activity near Mars and during perihelion could reflect predetermined survey protocols rather than simple responses to solar heating. This interpretation leads to romantic speculation about 3I Atlas waking up as it encounters the radiation signature of our star system, its artificial consciousness stirring after millions of years of dormant interstellar travel. The green coloration might mark the moment when dormant sensors begin functioning, while the rapid brightness changes could indicate data processing and transmission activities. However, The Scout scenario faces the same evidentiary challenges as the technological beacon hypothesis. The chemical signatures, thermal behavior. No evidence suggests information processing, directed communications, or other activities characteristic of technological systems. The exotic matter hypothesis proposes that 3 Atlas contains materials or operates according to physical principles unknown to current science. Theoretical physics suggests possibilities for exotic forms of matter with unusual properties. Dark matter interactions, modified gravitational behaviors, or quantum effects operating on macroscopic scales that could produce observable phenomena unlike anything in standard physics. Exotic matter could potentially explain 3I Atlas's unusual antitail through gravitational anomalies that redirect material flow or account for its enhanced outgassing through energy release. Mechanisms beyond conventional chemistry. The rapid brightening might reflect exotic phase transitions or energy storage systems that operate according to physics yet to be discovered. This explanation allows for natural phenomena that nonetheless transcend current scientific understanding, suggesting that 3I Atlas represents not artificial technology, but natural processes involving physics that human science hasn't yet encountered. The object could serve as an inadvertent laboratory for studying physical principles that don't manifest under conditions typical of Earth-based research. The temporal anomaly speculation ventures into the most exotic territory, suggesting that 3I Atlas might represent some form of information or matter transfer across cosmic timescales. Science fiction scenarios imagine the comet as a message or artifact from our own future sent backward through time using technologies that circumvent conventional causality constraints. This interpretation treats 3I Atlas's unusual properties as evidence for temporal manipulation rather than spatial travel between star systems. The object might originate from a future version of our own solar system, carrying information or materials intended for our current epoch. Its strange behavior could reflect interactions between future technology and present-day physical conditions. However, temporal manipulation scenarios require physics that not only remains unproven but contradicts fundamental principles of causality and thermodynamics as currently understood. No observational evidence suggests that 3I Atlas violates conservation laws or exhibits temporal anomalies beyond the normal relativistic effects expected for high-velocity objects. The critical perspective on all these exotic explanations emphasizes how often apparently mysterious astronomical phenomena receive mundane explanations once sufficient data becomes available. Pulsar discoveries initially generated speculation about artificial signals from advanced civilizations, but these objects proved to be rapidly rotating neutron stars. Fast radio bursts sparked similar debates before being traced to natural astrophysical processes. History suggests that 3 Atlas will ultimately find explanation within known physics, albeit perhaps involving processes or conditions not previously observed. The comet's unusual characteristics likely reflect the extreme diversity of conditions present in other star systems rather than manifestations of exotic physics or artificial technology. The value of exploring these speculative scenarios lies not in their probability, but in their ability to highlight just how extraordinary 3A Atlas truly is within the context of human astronomical experience. An object that can seriously inspire considerations of alien technology, living plasma, and exotic matter represents something genuinely unprecedented in our understanding of interstellar visitors. As 3I Atlas continues its hidden passage through perihelion, these exotic explanations serve as reminders of how much we still don't understand about the universe beyond our solar system. Whether the comet emerges from conjunction as a thoroughly mundane, if unusual object, or continues displaying characteristics that challenge conventional explanations, it has already succeeded in expanding the boundaries of what we consider possible for visitors from other star systems. Part 15: Countdown and Implications. The cosmic clock ticks toward a series of moments that will determine not only what 3I Atlas reveals about itself, but what it teaches us about the broader population of objects wandering between the stars. Each upcoming milestone represents a crucial test of our understanding, our observational capabilities, and our ability to extract meaningful science from phenomena that push every limit of current astronomical practice. October 3rd, 2025 marks the first critical juncture, 3I Atlas's closest approach to Mars at approximately 30 million kilometers. This encounter represents humanity's best opportunity to maintain surveillance of the interstellar visitor during the period when Earth-based telescopes begin losing sight of it. The mechanical eyes orbiting Mars will attempt observations never intended by their original mission designs, stretching technological capabilities to capture images and spectra of an object racing past at interstellar velocities. Success depends on variables beyond human control. If 3I Atlas maintains or enhances its current brightness levels, the Mars orbiters might capture detailed images of nuclear structure and coma dynamics invisible from Earth-based telescopes. However, if the comet fades from its September peak, even the most sensitive spacecraft instruments might detect only marginal signals, insufficient for meaningful scientific analysis. Late October brings the hidden climax perihelion on October 29th to 30th at approximately 1.36 astronomical units from the Sun's position. During these critical days, 3IA Atlas will experience radiation intensities that could trigger the most dramatic transformations of its entire solar system encounter. Maximum heating might activate volatile compounds that have remained stable throughout the comet's interstellar journey, potentially creating outgassing events spectacular enough to alter the object's fundamental characteristics. Yet, perihelion occurs almost exactly when 3I Atlas becomes most difficult to observe from Earth, hidden in solar glare that no ground-based telescope can penetrate. The cosmic irony places the moment of maximum scientific interest precisely when human observational capabilities reach their minimum effectiveness. Whatever revelations perihelion produces will remain largely hidden from direct observation, preserved only in whatever indirect evidence survives for later analysis. The observational gap extends through early November, creating a 4 to 5 week period when 3I Atlas effectively vanishes from human monitoring. This forced silence occurs during what theoretical models predict should be the comet's most active phase, potentially encompassing fragmentation events, dramatic brightness changes, or chemical transformations that would normally generate intensive observational campaigns. Reemergence in early December represents the next critical milestone when solar elongation increases sufficiently for Earth-based telescopes to relocate and track 3I Atlas after its hidden passage. The comet that emerges from conjunction might bear little resemblance to the object that disappeared in October, potentially showing signs of fragmentation, dramatically altered brightness, or evolved chemical composition reflecting its encounter with intense solar heating. The post-perihelion timeline extends the scientific opportunities through the following year and beyond. Jupiter approach in March 2026, while occurring at much greater distance than the Mars encounter might provide. Additional spacecraft observation opportunities as 3IA Atlas begins its final exit from our solar system. The geometry could allow distant observations by missions like Juno or the forthcoming Europa Clipper, depending on their operational status and orbital configurations. What we could learn from successful observations extends far beyond the specific characteristics of 3I Atlas itself. Interstellar chemistry analysis provides direct samples of materials formed around other stars, preserving information about chemical conditions present in protoplanetary disks throughout the galaxy. The carbon dioxide-rich composition already detected hints at formation environments unlike our local solar nebula, suggesting that planetary system chemistry varies more widely than previously imagined. Comet behavior studies under extreme conditions could revolutionize understanding of volatile release mechanisms, dust grain dynamics, and plasma physics in extraterrestrial environments. The anti-tail phenomenon challenges fundamental assumptions about how comet materials respond to solar radiation, potentially requiring new theoretical frameworks that account for electromagnetic effects not considered in conventional models. The scientific implications extend to broader questions about interstellar objects and their role in chemical evolution throughout the galaxy. 3I Atlas represents only the third confirmed visitor from another star system, but it's unusual. Characteristics suggest that the galaxy harbors far more diversity in small body formation than current theories predict. Each interstellar object studied provides crucial data points for understanding how common such visitors might be and what they reveal about conditions in distant stellar systems. Fragmentation analysis. If 3I Atlas undergoes breakup during perihelion, could provide unprecedented insights into interstellar object internal structure and composition gradients. And so, the story of 3I Atlas drifts back into silence. A visitor from beyond the stars, passing close to Mars, reminding us that the universe is alive with hidden travelers and mysteries we are only beginning to notice. Its journey is not ours to follow, yet for a brief moment we shared the same sky, gazed upon the same ancient fragment, and wondered about the worlds it left behind. As you rest, let your thoughts wander with it into the vast unknown, carried on the quiet rhythm of the cosmos. Tomorrow, more discoveries will come, more questions will rise, and more answers will reveal themselves slowly, like starlight reaching us across the ages. Thank you for joining Earth Analyst on this journey through time and space. If you enjoyed this story and wish to explore more hidden wonders of the universe, remember to like this video, subscribe to the channel, and gently ring the bell so you'll never miss our next cosmic voyage. Until then, may the stars guide your dreams, and may sleep carry you into peaceful galaxies of your own.